All right, welcome back, everybody, to the Additive Snack Podcast. I'm your host, Fabian Alefeld, and today we are diving into one of the most technically demanding applications of additive manufacturing, and that is, of course, gas turbines. And today we have somebody with us that lives at the center of innovation within that sector, and that is Dr. Ilya Fedorov. Ilya is a R&D project manager in the additive manufacturing organization of Siemens Energy. And Ilya and his team are truly pioneering additive manufacturing in the turbomachinery sector and have been pioneering that sector for a very long time. Really some of the first folks to really push the limits of additive manufacturing in production applications and in demanding environments. So therefore, in this episode, we'll dive into how additive manufacturing is really transforming the way that we look at turbomachinery. We'll talk about the reliability of systems. We'll talk about different types of applications. And we'll also talk about how far Siemens Energy is pushing additive manufacturing into their core applications. But of course, we'll also talk a little bit about Ilya's journey and how he has really witnessed the adoption of additive manufacturing within that sector. So therefore, without any further ado, Ilya, welcome to Additive Snack.
Fabian, thank you very much for inviting me. Really happy to be here.
Yeah, it's awesome to have you. We've actually had a few folks from Siemens Energy on this podcast, but today I'm really excited to dive deep into technology and into the applications with you. And I don't think there's anybody better to do that with me today. And before we dive deeper into your daily work, let's talk a little bit about your journey. How did you get into the turbomachinery sector, but then also what were your first touch points with additive manufacturing?
Okay. I have about 23 years of experience in gas turbines component design and development. In metal additive manufacturing, I'm about 12 years in. At the university, I studied in applied mathematics. That's my degree. And as I've been studying, my professor offered me an opportunity to work at the Central Institute of Aviation Motors, a mathematical modeling department. And that's that's how I met gas turbines. After graduation, I worked at major original equipment manufacturers, OEMs, in gas turbine world. That's Alstom Power, and a little bit of GE, and then Siemens Energy. That's my work experience. For additive manufacturing, I would say, I must say from the beginning that most of all I interacted with laser powder bed fusion. So that's part of metal additive manufacturing where I have most expertise in. I have done some work related to binder jetting and other types of additive manufacturing, but let's say I'm most versed in LPBF. My journey with AM, it started around 2013 during my employment at Alstom Power. Already at that moment, additive was recognized as an emerging manufacturing method. There were a lot of pioneering work by Siemens or also by GE. And I've been a mechanical integrity team lead at that moment in combustor department. And basically, everyone knows, I think, in gas turbine world that combustors is where application of metal AM started to be really the thing. So we were at the forefront. We wanted to explore this new technology. So that's how about 12 years ago I started working with additive. And then 8 years ago, I moved to Sweden and became a part of the additive manufacturing organization in Siemens Energy. So now I'm doing additive manufacturing full time. Yes, as Fabian mentioned, I'm an R&D project manager now, but it's not just Gantt charts. I still like to get my hands dirty, at least in figurative sense of the word, and I still do calculations and some design work, and of course, trying to get a hold of components with my hands as often as I can. So yeah, that's about it.
That's awesome. Yeah, I'm glad to hear that you still get to engage with the technology. I mean, so you mentioned 12 years ago where your first real touch points were additive and turbomachinery merged together. When was, and that's 2013, if I do my math correctly, which is quite early in additive years still. When was that moment where you realized the true potential of the technology in the turbomachinery sector? Was there a oh wow moment where really the light bulb went off?
Well, what I would say, I mean, even though it was quite already now a long time ago, even at that moment, there was already a lot of publicity from big players like Siemens using additive manufacturing to repair burners, and GE using AM to make additive fuel tips in LEAP engines. So, I mean, when such big players can turn additive into something that makes engineering and business sense, that kind of already proves that it's a valid tool. Of course, I mean, there's always thought like, million lemmings can be wrong, Yeah, so you have to have your own kind of motivation to do that. And for me, actually, I had such a moment you mentioned. Well, it was when we were designing completely new combustion system, and we developed a new approach, new design of combustion element, and then we sent it for printing. Then it was printed basically by end of the next day, and then in the next few days it went into the test facility to be tested and worked there successfully. And you may say that, well, I mean, that's rapid prototyping, that's not production. But for me, it was really the light bulb moment, because you see, when you have a metal part that is extremely complex and perhaps can only be done even by printing, or can be manufactured by other methods with a big effort, and you can get this part to be ready to be available within basically days, then for somebody who works in gas turbine world, that is something incredible. Because, I mean, any conventional methods of manufacturing, like precision casting, you order it and then you get your component maybe in a year, maybe in 2 years. And when the situation is like that, basically that kills all the motivation for innovation, for any like thinking outside of the box. Because, I mean, what if it doesn't work in 2 years? What you gonna do then? So you stick close to your known technology, your well-trodden path, but at the same time, then you are not improving. And when you finally see that you have this kind of a tool that can give you this power, I mean, that's incredible. That's a paradigm shift. So then I've understood it. And of course, when you have such a capable tool, even if it has some quirks, well, I mean, we're engineers. That's our job, to solve problems. So that's okay. We can solve whatever quirks are there. But the fact that you can do it so fast, you can be so flexible, that's incredible. So that's when I understood that additive is not just some toy, but I mean, that's something that can be a real production tool.
Beyond rapid prototyping, that's rapid innovation
Exactly.
to production.
Because I mean, if you can use it for rapid prototyping that can fulfill your function in in the test rig, then it's absolutely natural to think, okay, then we use the same tool to have a production component and manufacture it then with additive. Then you that's the point.
Yeah, that's awesome to hear. I mean, you hear similar stories from the space community, right? Where, of course, we know all the applications that now go into various space systems, but also that rapid innovation aspect of additive manufacturing that really allowed them to iterate really quickly and within a few days design a new combustion chamber and then test it within 7 days. is one of the key drivers also of of the fast growth of that sector.
Exactly.
Maybe before we go into some of those applications that you also just mentioned, for our listeners that aren't super familiar with Siemens Energy, can you give us a broad overview of the organization and then also how additive fits into just the broader innovation strategy of Siemens Energy?
Well, you see, additive manufacturing organization, I mean, it's a separate entity within Siemens Energy. And if you look up Siemens Energy additive manufacturing on the web, you will you will see on our webpage, quote, at Siemens Energy, we are at the forefront of additive manufacturing, completely revolutionizing how we design, produce, and even repair industrial components, unquote. So, and I mean, that's basically, that's what we do. That's what we do in our additive organization. And I would say in terms of innovation strategy, we have, I would say, 5 main pillars. So the first pillar is that we use additive manufacturing to improve performance, to have performance-driven design, to have upgrades in terms of performance improvement. And I mean performance improvement, not just like specifically like efficiency improvement of gas turbines, but in a much more general sense. So for example, enabling new fuels, green fuels, decarbonization. So all that improves our products. So that's our first pillar, the performance improvement. Then second pillar is strengthening of our supply chain. So you see, Siemens Energy is a major original equipment manufacturer. We provide various components, various parts to our customers, and it's very important that the flow of parts is not interrupted, because that would mean interruption of the business of our customers. So that's why we continuously monitor, the landscape of the procurement, and we're trying to understand what kind of risks we may have in this landscape. And I'm talking about risks, for example, when we have some critical part, and for that part we have a single source of supply, then it means that we are really dependent on our suppliers to provide us some raw elements of the parts. And then additive manufacturing is one of the methods that we use to resolve such situations, to provide alternative supply, even maybe with same function as the original component, but more readily available and available in-house. So that's how we do it. Then the third pillar, it's repair. So our, of course, additive journey in Siemens Energy generally started with repair of components with additive. So that's repair of burners. That started basically 12 years ago. But now it's much more than that. So we repair even turbine components, turbine blades, and those repaired parts go back in operation, and that gives us, first of all, ability to reuse the components, to be more sustainable, and also to drive our business forward. So that's the fourth pillar. And then finally, I would say spare parts on demand. So spare parts on demand is when some external customers would like to would like us to produce parts that are missing, where, for example, the supplier has gone out of business, so it's not our internal parts, but something our customers are interested in. And I mean, these are well-known situations. For example, like one company that had a fleet of boats, and engines on those boats were diesel engines manufactured by a supplier that went out of business. And this company had a choice to, let's say, completely replace all the engines on their boats, or just order externally somewhere the parts that need to be replaced in those engines. And this is where additive was very efficient to produce those replacement parts. And of course, that's very cost efficient. Yeah. And final pillar is, to me, rapid prototyping. So whatever we want to do, we want to test. It's very easy to get those parts with additive. So even if the part eventually will not be produced additively, for a test, it can be printed. But then, of course, you ask yourself a question, yes, as I did. So why then do you need to order this part in any other way but printing? So that's the fifth pillar. So these are the pillars. In terms of organization, well, I mean, we are a big team. Our major presence is in 4 countries: United States, United Kingdom, Germany, and here in Sweden. So in our additive organization, we have more than 200 employees, and we have over 50 LPBF printers and some other types of printers as well. We can claim that we have right now something like around 300,000 print hours annually on those printers. Yeah, which we believe is quite impressive. Yeah.
Yeah, that's super impressive. I think when it comes to machine uptime and availability, you guys are one of the leaders in the sector for sure. And I think also one of the players that understands true production environments the best. And I want to talk about that in a little bit. But before we do that, let's quickly double click on the application of turbomachinery. I think it's sometimes understated how challenging those operating environments are, and also how challenging the application itself is from a reliability and uptime perspective, right? I mean, these applications have to run for a long time and have to run reliably. So can you talk a little bit about just the gas turbine environment and what makes it actually a really challenging environment for additive applications?
Yeah. Well, you see, I may be a little bit biased here, and I apologize. My colleagues from other industries will probably fully agree with what I would say, but I believe that a gas turbine is the most complex mechanical system, let's say, ever designed by us humans. That's a big statement.
That's a good statement. That's a good statement.
Yeah. You see, why I think so? Because that's a synergy of multiple engineering fields in one area. So I would say that's aerodynamics, that's thermodynamics, that's combustion chemistry, that's solid mechanics, that's fluid structure interaction, that's material science. Everything is in there. And there's, because my education is applied mathematics, there's a lot of juicy mathematics throughout. So that's how I understood that gas turbine technology is a match for me from the beginning. But
sounds like it, yeah.
You see, why so many technologies and fields of knowledge come together in one place? Because components of gas turbines operate in extremely challenging environments, and at the same time, those machines. They are at the heart of very important industries like aviation, energy sectors, with extremely high reliability requirements. So at the same time, you have components that operate in insane conditions, and at the same time, those components need to be continuously available. Ideally, the engines need to operate with minimum intervention, minimum inspection. So that places huge demand on R&D, on development. And honestly, I mean, when we commonly want to refer to something which is something that is very, very technically difficult, we say this is rocket science. But I mean, if we look at rockets, I mean, at the heart of a rocket is its engine. And rocket engine, I mean, first of all, it has a lot of common components with a gas turbine. So, I mean, we have combustion chamber, we have, of course, turbo pumps that supply the oxidizer and fuel. But those turbo pumps, I mean, in fact, these are turbines. So that's the same technology. Of course, there's the Laval nozzle, which is a little bit special, but still. But all in all, those rockets, even reusable ones, they operate how many times? Perhaps like a few dozen times, I would say, at best. And that's a projection for the future. And we're talking about minutes of those engines running. And even though the conditions, of course, in a rocket engine are insane, but compared to that, a gas turbine has a lifetime of, let's say, 25 years, and it has to operate, thousands of starts without interruption, and as I said, ideally with minimum intervention, with minimum inspection, because this is what our customers want. They just want power. They don't want anyone to tinker with their machines. So that's why I believe that real rocket science is gas turbine engineering.
Yeah, you're not biased at all. But I mean, you make some really important points, right? I invite anyone from the space industry to come on the podcast and counter you.
I'm ready for a debate.
Okay, so I think that really explains the environment well, and also explains the requirements to additive well. Now, let's talk a little bit about the additive applications and the applicability of additive in gas turbines. Can you talk about the different types, or share an overview of where additive is seen in gas turbines today, and then we'll double click and deep dive into some of those applications.
Sure. So, well, first of all, I mean, I think in gas turbines, first applications of additive, that was in combustion. So systems that supply the fuel into the combustion chamber and provide good mixing of the fuel with air for efficient combustion. So reasons for such applications is that usually those components, those parts that are providing this mixing and injection features, so all kinds of burners, fuel injectors, they have really complex geometries. So and those geometries traditionally are difficult to manufacture. So I can show a couple examples here. So
awesome.
This is a printed gas turbine burner. And here, main thing is you can see there are a lot of contours inside, lots of walls. And here's another injector. So very similar thing. Main feature, it's like a nested doll. It's one contour inside the other contour inside the other. So what's the reason for that? That's because you have separate lines. You want to supply fuel. And very often it's not just one fuel, but it's liquid fuel and gas fuel. So you have two contours to supply fuel. Then you need to supply air to be mixed with this fuel. And then, because those components, burners, fuel injectors, they very often protrude into the combustion chamber, they are exposed to very high temperatures in the combustion chamber that are above the melting point of the material those parts are made of. So those external features have to be cooled. So you have to have additional contour, additional channels for cooling of the external surfaces. So now we've counted like four layers, and you need to assemble it all together. So if you manufacture it conventionally, this kind of design, it's usually assembled from dozens of small parts. Everything has to be welded. It's a very lengthy and expensive process. So additive provides a great way to print this as one piece. And that's basically what drew major players to use additive for production of combustion components very early. But there is another reason for combustion components to use additive. You see, combustion is a very very tricky process and very sensitive process. So testing of especially when a new combustor is developed, it's really challenging. And you have to go through many variants to land on the optimum combination of, let's say, on the one hand, low emissions, on the other hand, low pulsations, stable combustion. So it's really difficult to achieve. So with additive, when you design a component to be produced by additive manufacturing, then you can actually quickly iterate through versions, and you can test all those versions until you achieve the design you want. And eventually the design you want then turns out to be impossible or extremely expensive to be produced by conventional methods. So that's how additive makes its way into combustors. And just not to forget advanced fuels or green fuels. So we have a lot of efforts in our company overall to decarbonize the industry. So usage of, for example, hydrogen for combustion is extremely important. And then here, to even enable hydrogen combustion, that's another level of complexity of those burners, and that's again where only additive can deliver the necessary designs. So that's why additive is so popular in that area.
Is that because hydrogen burns hotter and therefore needs an even higher temperature resilience, or
exactly?
What's the
So you have to protect the walls. I mean, again, it's a similarity to rocket engines. So you have to protect the walls from the hydrogen attack. So and that creates even more complex design for a burner that uses high percentage of hydrogen.
Okay, so on the burner end, you therefore, I don't want to say by accident, but you got into additive by leveraging the rapid innovation potential, and you then ended up at a point where you really started to realize these burners are surviving gas turbine environments during testing. We're also making them more and more complex due to the fact that we have the rapid innovation potential, and then ended up at a point where additive became the obvious production technology to enable some of these next generation systems.
In parallel, we had successful experience of repairing conventionally manufactured burners with AM so that's a situation where this, exactly as I've explained, the front of the burner protrudes into the combustion chamber, and this front part over time gets oxidized, degrades, and then if you want to repair it conventionally, then you have to throw away, cut a significant portion of the part off and then weld the front piece again, because it exists as a separate part. But here, with additive, you can rebuild the missing portion of the burner, and you can not just rebuild, you can enhance it by improving the cooling system in front to prevent further outages and prevent further replacements of this component. And these parts went into operation quite a long time ago now, and now we have accumulated also quite significant experience of those repaired parts. And that is also supporting the introduction of full printed burners into operation.
Interesting. Okay, and therefore the benefits for Siemens on the one hand is you have higher performing systems, gas turbines. You have shorter lead times. You have faster time to repair, and it sounds like you have higher longevity of these burners within the environment. Is that correct?
Well, it's just it's a combination of all those factors. So you can trade efficiency for lifetime and so on. But yeah, it's always a combination of factors. But the thing is that overall these parts are as good as conventional ones, if not better.
Interesting. Awesome application. What else? What else you got?
Yeah, but that's not all. So I was talking about combustion. Then we have hot turbine. And hot turbine is where things get even more interesting because like the main thing in hot turbine is that components, plates and vanes, or as they're also called nozzles, those parts, when the plates are rotating, nozzles are stationary, but they operate in conditions where we have we have a hot gas at the inlet of gas turbine can be up to 1500 degrees Celsius. So extremely high temperature above the melting point of all materials in the turbine. And at the same time, because I mean, just generally gas turbines, I mean, they're based on thermodynamic cycle called Brayton cycle. And if you want to improve the efficiency of a gas turbine in Brayton cycle, the best way is to increase the combustion temperature. So on the one hand, you have the need to increase the temperature for higher efficiency. On the other hand, you have limitations of materials that simply cannot handle this, even with all the development of nickel superalloys that happened during the 20th century. So then what can you do? The next step is to introduce cooling systems. So to introduce a flow of coolant, most often as air, to reduce the temperature of components so that it can survive in such a hostile environment. And here, then the question comes, at what cost is this cooling done? Because when you are cooling the components, you have to take, I mean, most designs take the air from the exit of the compressor, so it's a compressed air. But then when this air is added to cool the parts in the turbine, it bypasses the combustor. And sometimes it also may bypass some stages of the turbine. So it's not working in the turbine. It's not generating power. So basically, we are wasting the potential of this air. And here, I mean, if we talk about, for example, nozzle guide vanes, that can be quite significant portion of total air going into the engine. So it can be from 2 to 4% of the air that enters the engine. It goes into cooling of one stage of turbine nozzles, for example. So then the question comes about designing very efficient cooling systems that use as little cooling air as possible, but they can reduce the temperature of the components to levels those components can handle. And this is where additive comes in, because you see, the trickiest thing is, I mean, when you are normally those components, gas turbine vanes and blades, they are manufactured by precision casting. And I mean, in any casting process, if you want to have a hollow part, if you want to have a part with some internal structures, that's where the casting process gets really complicated and involves a lot of special expertise, like manufacturing of casting cores, then removal of those cores. That's what makes this process so difficult, and that's why when you want a new precision casted guide vane ordered, it takes a few years to get one. So in this situation, additive helps, because with additive, it's as often said, complexity for free. So you can print whatever cooling system you design or your thermal engineers can design, and I mean, you can be super creative. And I would say the main tool of the trade for additive is what is called in-wall cooling or near-wall cooling technology. Let me explain. So we have this piece here, so little rectangular part. I mean, it doesn't look like much. This is a heat shield, a turbine heat shield. So it is installed on the internal surface of the casing to protect the casing from the hot gas. But as I said, here the gas on the surface is hotter than the melting point of this metal, so you have to protect the part as well. So this is of course 3D printed, and this is how it looks inside. I mean, I don't want to go into details of this cooling system, but the point is that embedded in this wall, you have an intricate system of channels which are not straight, they're wavy, and they have flow enhancement features in it. They have interconnections, so it's a really, really complex system. There is no way to cast something like that because these are thin channels within thick wall. So this is very beneficial. You have your cooling channel very close to the hot surface, so that's where how cooling gets most efficient. So when you don't have big distance between the coolant and the outer side, but at the same time you do not compromise the integrity of the wall because this channel still is only a small fraction of the total wall thickness, so it stays strong. So this is a great technology that can give you another, I don't know, 80, 100 degrees of temperature reduction that you will not get but by any other means. So, and of course, this is extremely important. So this technology, of course, I've demonstrated it on example of this simple heat shield. But here, for example, have 3D printed guide vanes, first stage, second stage, and those parts, I mean, they also have cooling system based on similar principle, based on in-wall channels, and with that, we can save cooling air and we can improve efficiency of our turbine nozzles.
Super interesting. What size are those channels on average?
That's about 1 millimeter.
1 millimeter on channels. Wow. And that's all air cooled through the intake air on the guide vanes as well as the heat shields. Is that correct?
Yeah, so I mean, they're cooled by air. So the air is not taken, I mean, it's not air coming from, it's not air directly at the intake. We need air with high pressure because then you eject this air into the flow path where the pressure is high. So if you do not use the highest pressure you have in the whole system, then the gas will flow inside the component. So you have to compress this air to the same extent you compress the air for combustion. But yes, it's the same air that, I mean, it's a portion of the air that entered the compressor through the intake.
Yeah, super awesome. How long? What was that development journey like? How long did it take Siemens to build confidence in additive, especially for applications like guide vanes?
Well, I would say this work started more or less when I joined Siemens, beginning of 2018. I think we had the first meeting in particular. This was one of the first components that we developed from end to end. And 2 years later, it went into operation. So I would say that's about a year of development, a year of production, considering qualification of all the post-processing steps and so on, some tests, verification, and then finally engine introduction. So yeah, that's more or less the time frame.
That's fast in gas turbine years. Huh?
Exactly. Normally it takes something like 4 or 5 years to complete a component of this level.
Super interesting. Okay, so we talked about injectors, burners. We talked about heat shields. We talked about guide vanes. Any other applications that are additively manufactured in production gas turbines today?
Well, I mean, we have dozens of components that we have industrialized. So we can have some. If we talk, for example, rotating components, we already have some smaller rotor seals and these kind of parts that go and operate like this serial produced parts. Then what else can I mention? So, for example, repair. So I mentioned repair of burners, but as I said, now we go further than that. So I can show this example. This is a turbine blade. And if you can see, the top of this blade has a slightly different color, and that's because this top is 3D printed. So the story is that these components experience degradation in the field. I mean, it's normal process. That's what happens over time due to very high temperatures, especially here at the tip of the blade. So then additive can be used as a technology to repair those parts. So basically to cut off the damaged portion of the blade, and on top of it, we print like a replacement piece. Again, we of course can print exactly same design as it is in conventionally manufactured part, but why stop at that point? We can, due to design freedom, we actually not just repair, but we enhance the component by printing improved cooling system at the tip that increases lifetime of it. So basically, yeah. So this kind of components also go into operation. Yeah, but as I said, overall, it's dozens of components. Some driven by supply chain resilience, some driven by performance improvement. But all of those are operating in the field as we speak.
Super impressive. I'm also most likely not mistaken that the qualification process of these additive components initially most likely was a challenge. How do you guys approach the qualification of new applications, new features? How many operating hours have you tested? For example, the guide vanes. What does that process look like to really qualify an additive part for production?
Well, I would say, I mean, in terms of qualification, so qualification of production, we follow our standard rigorous process that we have when we are qualifying new components of new design, parts produced with new technology. So, I mean, you see, just to explain where we are in our business, well, there is no equivalent of, I don't know, ASME boiler and pressure vessel codes in gas turbines. So, I mean, when I say ASME boiler pressure vessel code, I mean some kind of codified and very standardized way of manufacturing parts, such as pipes and pressure vessels. Yeah. In gas turbines, of course, there are international standards, ISO standards, but those more explain how to calculate efficiency, how to calculate, compare engines between different operational conditions, and so on. If we talk about design, those standards generally refer to experience of the original equipment manufacturer, OEM. So that's about the internal processes, internal requirements of OEM. That's what's driving the design requirements. At the same time, we also, I mean, most important thing about every design that we produce is that why do we have to follow our processes? Because that makes it possible to have insurance on the engines, to have those engines accepted by customers. So the very fact that we have rigorous processes and that we are following those rigorous processes is why we have our business. So from that perspective, if we want to introduce a new component, additively manufactured component, I mean, we follow standard process, like the standard design process, which you call product development process, PDP, with all the necessary reviews and gates on the way. And then in production, in qualification, we follow all the qualification gates, with involvement of expertise from across the company, and that's basically how it works. It's rigorous, it's time consuming and effort consuming, but it pays because then we are certain that we have assured the quality. So basically, yeah, when we do this qualification, we just follow a standard process that we would have followed with any other type of production. Yeah, you asked about specific durations. Well, I mean, it depends a little bit. So in some component, let's say, it's not a written rule, but what I know is that like the best practice is to have components verified at something like 15,000 hours in 2 engines, and sometimes at 1,000 combined. Sometimes it's in each. So it depends on application. But then there are some industries that require even higher amount of testing. For example, if we talk about oil and gas customers, if they have an oil rig in the sea, they do not care about efficiency that much, but they want the engine to produce power. Let's say with the highest probability, so to absolutely minimize all risks that this engine will go offline. And in that case, there can be some crazy requirements of tens of engines operating full lifetime or full operational period to prove that a new component can be implemented. So that's sometimes it gets tricky. But here I would say when we proceed with verification and validation, verification we do first of all with rigs. Rig tests. So it means instrumented engine tested in controlled environment. So we described such a test in one of our papers from ASME Turbo Expo 2023. So when we were showing how we have installed several stages of additive manufactured components into a gas turbine and tested it. And we had instrumentation with thermocouples and so-called thermal crystals. What it gave us, then we were able to verify the temperature levels we had in the components and confirm our expectations from design what those temperature levels will be. So basically verify the efficiency of our cooling systems. So that basically are the driver for introduction of AM in those components. So yeah, that's very important. But then if we talk about lifetime verification, then you really need to have those parts in an engine in a running condition. And here I would say most important is to have a good collaboration with your customers. So to have a willing customer that would be ready to accept parts for testing, for validation in his engine. So of course, let's say getting some early benefits of performance improvement coming from advanced parts, but at the same time, being ready for our extra scrutiny, being ready for us inspecting this engine some extra time to be certain in condition of the parts. So that's why it's very, very important to have such relations with customers. And I would say we have these good examples. So components which I've been showing. So these were tested here. I would say these parts spent full operational period. So basically it's about 30,000 hours in the engine. So you can see by the color of the ceramic coating that those parts are really engine run. But at the same time, you can see the condition of the parts is basically good as new. So the parts worked really, really well. So yeah, and that's thanks to our good relations with the customers, we were able to obtain this experience and advance our additive course.
Yeah, and also prove to the rest of the industry how reliable that technology can be in highly, highly demanding end-use applications.
Just wanted to include this little self-promotion. So we have some papers published in ASME Turbo Expo proceedings on verification and validation of those parts in engines. Please feel free to look for those, and hopefully soon there will be also journal publication with some more details. So yeah, that's an interesting, really interesting example of application of AM in turbomachinery.
Yeah, super awesome. Make sure to check it out. We'll try to also maybe link to it in our show notes. Now, I see a picture behind you of some powder particles, and of course, additive is also a materials game. Now, how do you, as Siemens or as Ilya, approach material selection, research? New materials obviously unlock new applications. So what's your whole approach to materials?
Well, materials have extremely important role in development of gas turbines. So as I mentioned, to improve efficiency, we want to increase the temperature, and then it means we need more reliable materials that can handle higher temperatures without losing integrity and function, let's say. And therefore, basically, it's always about wishing for materials that have a high temperature characteristics, such as creep resistance, thermomechanical fatigue resistance. So it's resistance to cyclic load, when not just load cycles, but also temperature cycles from low to high and back. Resistance to degradation in high temperature conditions, such as oxidation and high temperature corrosion, and many more damage modes that can happen to gas turbines. So you always want a material which is better. And of course, here we want to develop materials that are at the level of conventional cast materials, like this really high strength, high temperature alloys. I would say one thing to mention specifically about AM materials is that, at least according to my experience, in AM, the cost of powder, of course, it is important. It's an important portion of the overall cost of printed component, but it's less critical than the cost of raw materials when we talk about conventional precision casting. So it's actually a positive thing, because it means you should not worry that much about choosing a higher grade material for printing. Because you basically the costs of printing, the machine hours would cost you more than like higher fraction of the total cost than the powder. So that would mean that if you have a material that you can reliably print, then you basically select the best possible material that you can reliably print for an application, and you're fine. So that's how it works.
Okay. And then what role does process development, so process parameter development, play for you guys? It's obviously a key part of material development, of application development. How are you preparing your teams to also be on the cutting edge of really pushing parameters for specific applications or for productivity? How are you approaching that aspect of development?
Well, that's a significant portion of what we do. So the development of process parameters, that's our technology team is focused on. So here you see the main idea is to optimize the process parameters. First of all, to achieve best possible microstructure with respect to all microstructural, let's say, indications, such as, for example, pores or microcracks. So you tailor the print parameters to minimize those, so to get those as low as possible. But on the other hand, then you need to consider also macro features, like, for example, risk of cracking during printing, like solidification cracks, or risk of cracking during subsequent heat treatment, like strain edge cracking. So all of this comes into like the same equation, and the technology development team is focused on like optimizing, getting the most out of the material from process perspective, to minimize all the negative effects, and basically that's the aim. And once that is done, then we proceed with thorough mechanical testing to determine the properties. Of course, spot checks of properties are done already during parameter development, but then once the parameters are fixed, then we proceed with like full scope testing to determine all, for example, creep properties, thermomechanical properties, oxidation data, and so on. And of course, you do it when you have already fixed your production parameters. Otherwise, you have to do a very, very expensive testing all over and over again. So that's how we do it. But yeah, as a result, we managed to achieve good certainty on parameters of and properties of printed materials we use for design.
Yeah, and you guys are really on the cutting edge of of really pushing the limits of the technology, which also makes you a really good person to talk about still the limitations and challenges that additive potentially experiences. From your perspective, what are still some challenges you're working on to continue to bring additive further and further into future applications?
Oh, well, there are different types of challenges. So some challenge, I mean, I touched upon when I was talking about the requirements for introduction of EM components to customer engines. So it's about collecting more and more operational experience. When we have convinced ourselves that those components work well, that's good. But then you have to convince your customers, you have to convince insurance partners, and that's why you really need a lot of experience. And this because the industry is has certain inertia. So we are talking about engines that work for decades, sets of components that work, let's say, undisturbed, ideally for like 5-10 years. That's why it takes time to get this information, to get this experience. But I mean, we are getting there. As we speak. So we are gathering more and more data. So that's where we are advancing. But at the same time, yeah, this is still a challenge. In terms of technology, well, you see, ideally, would like to have EM materials that have properties, let's say, equivalent to conventional cast, of course, advanced precision casting alloys. So I'm talking about advanced nickel superalloys, especially ones which are considered, poorly weldable. So of course that's not a universal characteristic, but usually if an alloy is easily weldable, then because printing LPBF, I mean, is but by nature is a kind of a welding process, then usually you get good results with printing. But if alloy is poorly or not weldable, then it's difficult to print it, or difficult to get parts through the post-processing steps without developing negative consequences. So that's where it gets tricky. And here, I mean, main direction, main progress that we have achieved, that we are not actually trying now to print something that doesn't print well. We are trying to develop materials that would have properties equivalent to those common very high temperature alloys in casting, but it's not going to be the same materials. It's just going to be materials that are designed practically from scratch, optimized for printing, but have properties equivalent to those common casting alloys. So that's what we believe is one of the key directions for the development, and we have some really, really good results on this road. So which I hope quite soon we will be able to show and present. Well, what else?
And maybe just to touch on that, I think that's a really important point, right? That we're now at a point in the industry where we're not just replicating conventional alloys, but we're developing alloys specifically for the manufacturing process, laser powder bed fusion in your case, for specific applications, for specific post-processing procedures, and then also for new innovations of the manufacturing process, like, for example, new light engines, such as beam shaping, that also unlock new alloys and new alloy development. So it's a very interesting point in time
Exactly.
where these new applications then are being unlocked by these very specific additive alloys.
Yeah, that's true. Well, I mean, then I would say, I mean, as any manufacturing process, so 3D printers are our main tools, and we are currently working to get, let's say, most reliability, repeatability from the printers we have. So yes, we push the printers far, and yeah, but we still want to those printers to be fully reliable and predictable. So that's also something we are working towards. Yeah.
Now, you talked about new materials. You talked about also rotating components. What is the next target you've set for yourself when it comes to applications? What's the holy grail of applications that you want to get to?
Well, I mean, generally, if we think about the future, so once again, it's a little bit inertial, or our industry has some noticeable inertia. So when sometimes you think, yeah, what's you gonna do in 5 years? Well, in 5 years, we will see the condition of components that we just placed into one of our engines. So that's a kind of planning. So maybe a lot can happen in personal life in 5 years, but it would be the same set of guide vanes running in a particular gas turbine. So that's important to remember. But of course, I mean, first of all, we look towards like getting more experience with the parts, especially now when we have a lot of additive components in the field. So to gather this experience and to learn from that. Well, overall, I mean, generally, we are always on the market looking for new AM technologies that we can apply in our business. So, for example, looking for larger machines, because that would just allow more business cases. We have some large components in our fleet that would be good for printing, but currently simply do not fit into the size of a printer. Then, of course, any other new technologies that offer higher productivity, that's also something that we are looking for. So once higher productivity technologies can be really industrialized, we would be happy to use such things like high productivity machines, whatever. Yeah. And yeah, as I said, getting most reliability and repeatability from the printers we have.
Okay, and then you touched on it a little bit in the beginning of our conversation, but if you look at the next generation of gas turbines, how is additive shaping that? Do we see a future? You mentioned new fuels like hydrogen. What other pieces of innovation or optimization is the market demanding for that you're also trying to solve with or without additive?
Yeah. So I would say the general thing is that currently, at least in our company, in Siemens Energy, additive is considered as one of potential methods of manufacturing components, and also as an enabler for improved designs. So when whatever discussion happens about development of some kind of new products, additive, and I'm quite happy about it, additive is included into this discussion as one of opportunities, something to be considered, let's say, on a concept level when a concept of whatever product is being shaped. So, and this is how additive, I would say, already now influences practically all that we do, because even if at this concept phase, the decision is eventually taken not in the favor of additive, but let's say the decision is taken to make this product with conventional or some other technology or whatever, still additive offers are being discussed, and they're pushing our, let's say, internal competition forward. And as a result, our company benefits from that. Yeah. But of course, then there are some areas, as you just mentioned, for example, decarbonization, the fuels like hydrogen, where it's already a fact that you need additive to be successful. Then turbines is really hot turbine components, really emerging market, and we are getting more and more examples of parts additively manufactured being used. So yeah, overall, additive is a huge driving force for innovation in Siemens Energy for new components.
So, and we on the sidelines will keep our eyes open and watch the innovation that comes out of Siemens Energy. Ilya, it was really awesome to have you on the show. I am really glad we got to dive deeper into the different applications and also into the impact that additive has on Siemens and the Turbomachinery sector. Thanks for leading the way and showing others where to go and how to get there, and also for being so open with some of your approaches and also learnings that you've gathered from your time at Siemens, and also just in general from the history that Siemens Energy has in the additive manufacturing sector. So thanks for being on the show. It was great to have you.
Thank you for having me, Fabian. You're a great host. Thank you so much.
Appreciate that. And also thank you out there for tuning into this episode. Keep an eye out for Ilya's papers that he mentioned, and keep an eye out for just in general news from the Siemens Energy folks. As I mentioned, they're always on the cutting edge of the technology. This was the Additive Snack Podcast. If you like this episode, share it with a friend, a colleague, or anybody who wants to learn about additive or turbomachinery. I'm your host, Fabian Alefeld, and I will see you next time.